now let's go ahead and take a quick minute to talk about another feature of C++ called templates. Often in programming, we might find ourselves needing to do very similar operations to various data types, right? So for instance, we may need to write a function that will give us the maximum value of a set of integers or the minimum value of a set of integers, or we may also want to perform those exact same operations on a set of characters, for instance, or a set of floats, or a set of shorts, etc. The problem with this basically is in order to do the comparisons correctly, we need to write an entirely separate function with a separate name in order for the comparisons to be done properly. And that's simply because different data types have different sizes. The data may be interpreted differently, which means if you would try to write some generic function that would compare a float to an integer, you're going to get bad data back out of that function because that's not a valid comparison. You need to compare the same types to each other in order to get the correct comparison. So for instance here, if we look at this program I just opened up, we have two functions in here. We have a float find max and we have an int find max, right? Where the types being compared in this function are floats and the types being compared in this function are ints. What we're going to notice, however, though, is that other than the declaration of the data types, such as int and float here, the code is completely identical. There is literally no difference between these two functions. I copy-pasted them and changed the data types. That's it, right? So if we need to do this quite often in our programs, this introduces a large opportunity for duplication of code, which is not necessarily a good thing, as well as the ability to potentially introduce new kind of subtle errors into your programs, which you might not catch right away, right? Just think if you forgot to change one of these data type references, that could throw the whole thing off, and all of a sudden we're getting bad data out of our program and we don't know why, right? So what we need is a better way to do this, or a much more generic way of doing this, which is actually what C++ allows for us to kind of take into account with the template features, right? So what a template allows us to do is basically kind of define a generic type that the compiler will then fill in for us later, right? And it will infer what it needs to fill in by kind of how we use that templated type. So if we want to declare a template, basically what we need to do is we would first type out template type name T, right? What this is basically saying is anywhere we put an uppercase T by itself in the program, that's going to represent some type name, right? It's going to be a placeholder for where you would normally see int, or you would normally see float, or you would see string, etc., 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 right? This is declaring a placeholder that we are going to put in other locations of our program, right? And just so you know, this T would not have to necessarily be T. We can define what we want this to be. We could call this type name. We could call this my type, etc. Whatever we want, we could put there as long as it's not reserved or has some other meaning in the language. But for our cases, what we're going to do is we are just going to call this T. Right? So then after we declare our template type, we can start defining the rest of our function as we normally would. Now what we are going to see here is, again, I have the exact same function that I had open in the other file, findmax.c. Right, so over here I had our original functions, right? Float find max, float float float, compare the numbers and return the maximum value. Now again, over here I have the exact same function yet again. The difference here is I have replaced all type references with that T. So instead of seeing int or seeing float or seeing char, you instead see T. So if we look at what this function prototype is kind of telling us, it is saying that we are going to find the max of 3 given values that could be of any type, and the thing we're returning back from this function is the same type as the values that are being passed in, right? And then we can also declare local variables that are of that template type, right? So here we define maxval as being t, right? So this means that the compiler will come back in and fill in this information for us and generate the correct code for us without having to deal with any of the plumbing ourselves. Right, so in order to give the compiler that kind of information, it's going to go ahead and look and see how we use this function later on in our program. So if we look at the main function, you can see I declare 4 integers, I declare 4 floats, and then I call find max, right? And I call find max with my integer variables, and I call find max with my float variables. Now the compiler is smart enough to understand that I'm calling it with 3 integers here, so when it's compiling it comes up and it basically copies our little function that we wrote here, and then it rewrites it to look exactly like our int find max function down here because it knows we were trying to use integers there, right? So it takes that function, fills in the t's with anywhere it sees a t, it fills it back in with an int, and all of a sudden we have our integer comparison function. Now it's also important to note that behind the scenes, the function's not necessarily called find max anymore. It's going to be named something similar to int find max or some other, conglomeration that the compiler knows and understands that this is the integer comparison function. Right? So we went ahead, we called find max with our integers, and we printed out the maximum value. Now we again go back, and now we call find max again, but this time we're passing it our float values. Right? So again, the compiler understands that x, y, and z are float types, so it again goes back to our template, makes another copy of it, and again replaces all of the t's with the actual type we want to use, which is in this case float, right? So anywhere it finds this t, it replaces it with float, it renames it, and now it knows that this is the float comparison function that it should actually use, right? So in the end, our program ends up looking very much just like the code you see to the left, but us as users and programmers only had to write this one generic templated function, right? When you talk about a template, it's the outline of something that would be filled in with other things later, but it's generic enough that it can be reused over and over and over again, right? That is exactly what's happening here. For us, from our perspective, we write the template, and then the compiler goes ahead and generates the actual code for us behind the scenes without us even knowing it. That's kind of the really cool part about the templates. As long as the compiler has the information it needs to kind of fill them in, this works, and it's very simple for us. Now granted, templates are kind of controversial sometimes because they do generate multiple copies of the same code, just with different types, so it can kind of bloat your program, but depending on what you're doing, that may be a worthwhile trade-off, okay? So that is templates at its simplest form. So we can use templates with functions, and we can also use templates with classes, right? Just like we would potentially have functions that operate on different types of data but perform the same operation, we might have different types of classes which will operate on different types of data, but again, the operations are kind of agnostic of the data. We just don't want to have to rewrite our class every single time we want to implement some new data type, right? So I'm going to close out of this real quickly, and now let's look at an example class. What do they call that? maxclass.cpp. Right, so this is a pretty straightforward class, which is an example in the Zybook C++ book, if you've ever looked at that. Right, it's a class called TripleInt, and basically it has 3 variables that are set from the constructor, and then all it does is basically print those variables and tell me what the min item is inside of those variables. right? And the function here, its constructor just assigns item 1 to I1, item 2 to I2, item 3 to I3, which are the parameters that are passed into the constructor. And then we just go ahead and print those values off, right? And if we look at how we use it in our main function, we just create an instance of that class, passing it our parameter values, and then we go ahead and print those values off. If we want to look and see what that looks like, we'll compile that quick. And as you can see, it prints 30, 40, and 50 out. Right, now again, let's say we want to extend this class to handle more than just integers for whatever reason. Right, if we were going to do that, right, we would basically have to make a copy of this class, and then for each type we would need to call it like triple float, and then we would go down here, and then we would have to start changing things to float. Every integer would change to a float, etc., etc. Right, but that's kind of not as much fun or not very cool. So what we can again do is now we can use templates to make this generic for us. So if we open up my actual template one, right, you can again see that the class is exactly the same as it was before, but now the difference is before the class definition we have declared a template type, which again we've just called it T. So now wherever we would see int or we would see float, we again just replace it with T to say that this is something that will be filled in by the compiler later. Right, so we have T min item instead of having int min item. We have T item 1 instead of int item 1, etc., 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 right? And then we can go ahead and we can start writing our actual class definitions, or our actual implementations of the class functions, such as the constructor. Now, the one extra thing to be aware of when you're doing templates inside of classes is whenever you declare or you work on implementing a class member function, you need to also include, if you are implementing a class member function of a templated class, then when you define the actual function for that class, you still would end up with the same, name of class, : name of function, but now you have to prefix every function with template type name T, and then you need to say name of function, angle brace, T, or your template name, whatever you called it, angle brace, right? This is to make the compiler aware that this is a function that is inside of a templated class and it requires this extra information so that you can go ahead and use the templated names inside of the function, right? So here we have template name T. Our name of our class is actually triple int, template, name of function, and after we have set that up, we can start using the template name inside the definition, right? So now we can have TI1, TI2, TI3, instead of having int I1, int I2, int I3, etc. And you need to do that for every single member function that you're implementing, especially if they are using templates inside the definitions. Now you might ask, if in fact my function does not actually use any of the templates, right? It's just printing some random thing, or it's kind of just really doesn't do much of anything in the function. Do you still need to put template type name T at the beginning of the function? And the answer is yes. That is because when we define our class as template type name T class triple int, what we've actually done is more or less behind the scenes renamed the class, where the name is triple int angle brace type of the class or type of the template, and then angle brace again, right? So this is actually the new name of that class if we are defining some member function, right, for this syntax. So in order to be able to use angle brace T, you need to put this before your function implementation. So this is basically just something that's always attached to your functions once you start using a templated class. Right, so after you've defined all of your class functions, the next big thing is, okay, how do you actually give the compiler the information that it needs to actually kind of build that template for you? And the answer lies in those angle braces that you saw in the function implementation. Right, so now basically what we're saying is we're saying create an instance of the triple int class, which is of the int data type. Right, so here we basically will, again, the compiler will copy and more or less copy and paste all of this code that we wrote for the class and replace any of the t's it finds with int. So we now have an instance of that class that can handle integers. In our other line, basically what we're doing is creating an instance of the triple int class, and we're going to make it handle float data types. Right, so it goes through, copies all the functions again, replaces the t's with floats, and then you're off to the races. Right, again, this works with pretty much any data type that supports the operations that we're performing on it. Right, so if we were going to run this, g++ max class underscore t, and we run it, and you can see, okay, we got 30, 40, and 50, and then we have 30.02, 40.1, 50.3342, etc. Alright, so this is really cool that we can create classes that handle different data types without really needing to write any specialized code, just because we can make use of these templates. I'm trying to think here, is there anything else that I wanted you to know about? If you were wondering, this is you'll see this used quite a lot with the standard template library functions, right? So templated library. If you use vectors or you use the STLQs, etc., or stacks, so on and so forth, right? You need to use that syntax that I showed you here, right? So, not G++, yeah, not that one either. Right, so if you were using an STL class, like the vector, right, if we were creating a vector, we would say we want a vector, and then we need to tell it what type of vector we want. So we want a vector of ints, right? So this is the exact same mechanism that the STL library already uses. It's just how we would go ahead and take advantage of it for our purposes in this class. Right, so if you have any questions, please let me know. We'll kind of be using templates on and off throughout the duration of this class, so as you get more experience with them, things become a little clearer with them, etc. Again, you don't need to know the nitty-gritty details of how templates work, you just need to be able to understand how to use them in your code. Right, so again, if you have any questions, don't hesitate to ask me. And that's it for this video.